Okay, the mathematicians are not still sure that if e plus pi is irrational or e pi is irrational, but we know that at least one of them should be irrational, and the goal of the videos would be prove that statement. Okay, so but first of all, let's see why we are not sure that e plus pi is irrational, because some of you might think that obviously if we are like adding two irrational numbers, we should get an irrational number as result, right? So yeah, we get 3 root 2 and this is irrational. But that's not always the case, because let's say if you add root 2 with negative root 2, you get 0, which is rational. So even though you are adding two irrational numbers, you can get a rational number, right? And again, with the product also you can definitely get, let's say you might want to multiply e and 1 over e, both of them are irrational. But yeah, we get answer as 1, which is rational, right? So yeah, it's not necessary that the product or sum of two irrational be a rational number. So yeah, there's not really any proof till now, like if these two are irrational or not. Okay. Also, there is an elegant expression where the combination of irrational is beautifully rational. That's e to the power I pi is equals negative 1. Even though we are combining irrational and imaginary numbers, we get like a rational number, right? So yeah, that does happen, and so like there's no need to be surprised about this. Okay, now let's go to the proof that at least one of them, either just one of them or both of them are irrational. We are going to prove that. We're going to prove that at least one of e plus pi or e pi is irrational. The proof is beautiful, and I do believe you will enjoy this. But before we go to proof, you need to know something about e and pi. We know that these are irrational numbers, right? But more than irrational, these are also transcendental numbers. Transcendental numbers. Now you might wonder, what are transcendental numbers? Transcendental numbers are those numbers which are not algebraic numbers. Not algebraic numbers. Okay, again, now what are algebraic numbers? Now, algebraic numbers are those numbers which can be expressed as a root of a polynomial with rational coefficient. I will rather than explain what that means. Algebraic, I mean, most of the numbers are algebraic. Algebraic numbers are those numbers which can be expressed as a root of a polynomial with rational coefficients. That means rational number coefficients. Okay, so let's say I have a polynomial with rational number coefficients x squared plus 5x plus c. We know that the roots of this polynomial is just negative to negative 3. For that, you just need to equate this to 0 and then solve it, right? So yeah, negative to negative 3 are roots of a polynomial with rational coefficients. So therefore, these are algebraic numbers, right? Similarly, all the whole numbers, all the integers are algebraic numbers, right? All the rational numbers are algebraic numbers. Also, not just rational, even the some of the irrational numbers are also algebraic. Not all, but some of them. Just like if you have x squared minus 2 is equals to 0, x squared is equals to 2. So this is a polynomial with rational coefficients, right? Now if you want to find its root, that will be plus minus square root 2. So this is also a root of a polynomial with rational coefficients. So that's why plus minus square root 2, both of them are algebraic numbers. And not just some irrational numbers, also some imaginary numbers are also, I mean not all, but most of them. Imaginary numbers are also algebraic. So I can write it as x squared plus, this is an algebraic this is a polynomial with rational coefficients, right? X squared plus 1. If we try to find its root by equating it to 0, this will be minus 1, x is equal to plus minus I, right? So yeah, plus minus I is also a root of polynomial with rational coefficients. So yeah, plus minus I is also an algebraic number. So yeah, we see that there are a lot of algebraic numbers. So most of the numbers, even though they are algebraic, I mean, even though they are irrational or imaginary, they can be algebraic. But yeah, Using a branch of math called algebraic structures, we have already proved that e, pi are not algebraic numbers. So yeah, that proof is beyond the scope of this video, but yeah, it's already proved by mathematicians are not algebraic numbers. That means they cannot be written as a root of a polynomial with rational coefficients. That means there's no such like ax to the power n bx to the n minus 1. There's no such like a polynomial whose root will ever be like e or pi. There's no such polynomial. Okay. So now, we are going to use this fact to prove our statement. We are going to use this fact or to prove our statement that at least one of them. So let's see how we can do that. Okay, so till now we know that e and pi are transcendental numbers, so that means they cannot be expressed as a solution of a polynomial with rational coefficients, right? Also, this definition can be extended over, even though I say over here the rational coefficients, I can also say that integer, because let's say if any number is a solution to, let's say, this expression where there's not an integer but a rational coefficients, right? So yeah, like the solution to this equation will also be solution to like 3x square plus 2x plus 18, right? Their solutions will be same, right? Because yeah, if you get to 0, you can multiply both sides by 3 and get this one, right? So yeah, like like in more formal definition we say it as integer, but rational also works. So now let's go to proof. We know that e and pi cannot be a root using the fact that they're transcendental. They cannot be a root to a polynomial rational coefficients, right? But yeah, let's try to make them a root. Let's try to obtain a polynomial where the e and pi will be a root. Okay. So yeah, let me just expand this, and we get a polynomial. This polynomial over here, whose roots are e and pi. Okay. Now we know. Let's assume for now that this one we're not done. This one is like automatically irrational. Let's assume that these two are also rational numbers. Let's assume that both are. I mean, let me just say rational numbers here. Okay, let us assume that this is rational. Okay, first of all, we are assuming that both e plus pi and e pi are rational. So if that is the case, if all of these are case, now we have successfully expressed e and pi as a root of a polynomial with rational coefficients, right? If we make that assumption, if we assume both e plus pi and e pi are rational, we get to a contradiction. We get to contradiction that e and pi are roots of polynomial with rational coefficients. That is, e and pi are algebraic numbers. But clearly they are not, right? But clearly they are not. They are transcendental. They are not algebraic. It has already been proved. So yeah, we get to a contradiction, right? Over here we get to a contradiction. So a contradiction means that we had started with a wrong claim. That means our assumption was wrong. So that's why we got to a wrong result. So yeah, so contradiction means that our assumption was wrong. So yeah, so we cannot assume that both of them are rational. So that means at least one of them has to be rational, right? Like either just this one has to be rational, or this one has to be rational, or both have to be rational. So since assumption was wrong, so that means both of them cannot be rational. So not any, like at least one of them. I mean, if both of them cannot be rational, then either one of them is irrational or both is irrational, right? So at least one of them has to be irrational. And yeah, that's how we prove this statement. So we just try to make a polynomial where e and pi are roots, and then definitely we get to a result that if both are rational, then e and pi become algebraic, but clearly they are not. So therefore, at least one of the e plus pi or e pi has to be irrational, and that proves it. That proves the statement. So this was the really elegant proof, and I learned it from the Putnam session by Law. Definitely, I want to give credit to him. Right, definitely you can check his like Putnam lectures on YouTube. They are really good. I'm enjoying them, and I loved this, and I thought of sharing this to my audience as well, so that they can further share to their friends, and from again their friends, other friends, so that everyone would like get the chance to enjoy this beautiful proof. So this was interesting. Hope you enjoyed it. Thanks for watching, and I look forward to seeing you in the upcoming videos too.